Okay, in 1.6, we're going to talk about determining limits using algebraic manipulation. So in the last section, we kind of just breached the surface of how to evaluate limits using basic algebra and the limit laws. Now we're going to do a little bit more complex problems. It's a picture of our friend Sir Isaac Newton, father of calculus. So let's jump to it. Okay, first property, if f of x equals g of x and x does not equal a, then the limit of f of x as x approaches a is equal to the limit of g of x as x approaches a, provided the limits exist. So all this is saying is that if you have a function that's equal everywhere but at a single point, a, specifically at our limiting value, then the limits as x approaches a will be the same. So you could have like okay, this is function f, and then I could have this is function g. But let's pretend for g for a second it's not defined at a, but they're the exact same everywhere else. Well, then the limit as x approaches a will be the same for both functions. All right. And I'll talk about how that applies to this example that we're about to do. So first we'll use the old-fashioned method was let's try and use a table in our calculator to evaluate this limit. And then we'll do it algebraically, right? Okay. So go to y equals, I'm going to do x squared minus 1 in parentheses, oh, come on, x squared minus 1 over parentheses x minus 1. And the limiting value that we're approaching is 1. So we want to get closer and closer to 1. Let me delete all these. Let's try from the left side. If I want to get closer and closer to 1, I could start at 0, 0.5, 0.6, 0.7, 0.8, 0.9, 0.99, 0.99, whoa, 0.999. And it does look like my y values are approaching 2, right? Let's try it from the other side. So maybe I'll start at 2, 1.5, whoops, 1.2 rather, 1.1, 1.01, 1.001, and so on. And it does look like I'm getting closer and closer to 2 again. So yeah, if we were making an educated guess, I would probably say that this limit is 2. So now let's try and use some algebra to do it. If I just tried to use the limit laws that I had from the last section, I would start out this way, right? I would make this a quotient of limits. And then we would break it up into smaller pieces. So I would have the limit as x approaches 1 of x squared minus the limit as x approaches 1 of 1 over the limit as x approaches 1 of x minus the limit as x approaches, 1 of 1. And that would leave me with 1 squared minus 1 over 1 minus 1, which is 0 over 0, which is undefined. So that doesn't get me a limit. Specifically, it doesn't give me a limit of 2, which is what we kind of saw in our calculator. All right, so why is that? So 0 over 0 isn't undefined. It's actually called indeterminate. And all that means is that in the current form, I'm not able to evaluate the limit. So I'm going to try and do a little bit of algebraic manipulation to see if I can evaluate the limit. Let's go back up. I'm going to erase everything. We still know from our table, or we think it's pretty plausible that the answer should be 2. Well, notice that the numerator is a difference of squares. And if you don't remember what that is, that's when you have something like a squared minus b squared. That will always factor out in this form, a plus b, a minus b. So I can factor my numerator. I can say the limit as x approaches 1 of x plus 1 times x minus 1 over x minus 1 in my denominator. Now, this is where this property kicks in. Notice that I can cancel these. That's going to leave me with the limit as x approaches 1 of just x plus 1. And I'm okay saying these are equivalent. What I'm not okay with, I'm going to make a note off to the side. It is not true that x plus 1 times x minus 1 over x minus 1 is equal to x plus 1. Those are not equal. And the reason being, in this one, x equals 1 is fine. That's in the domain. In this one, x cannot equal 1 because it would make the denominator 0, right? So those functions are equal everywhere except at x equals a, which means their limits will be the same. So I'm okay with using an equal sign here, because here I'm talking about the limit as x approaches 1. I'm not okay with using an equal sign here, because they're not equal for every value of x. They're equal for every value of x other than 1. All right, and since I'm just talking about what's going on as I approach 1, their limits are equal. Well, now I'm taking the limit of a first-degree polynomial, so I can just use direct substitution. I can just take my limiting value and plug it in for x. Once you do that, you can drop the limit notation. So now this is just 1 plus 1, which is 2, which is exactly what we got in our calculator. All right, so that's kind of what we're doing in this section, is trying to come to situations where we're not able to evaluate the limit because it's in an indeterminate form, and then manipulate the function algebraically to get it in a form that we can evaluate the limit and can use a direct substitution. Okay, so find the limit as x approaches 1 of g of x, where g of x is defined as this piecewise function. So this one shouldn't be too bad. It's just trying to be tricky. So it's defined as this x plus 1 everywhere except at x equals 1, it's defined as pi. So that leaves us with a little hole and then a point above the hole in our graph. And so as we approach 1, remember, we don't care what's going on at 1. So in fact, I can say that that limit is going to be equal to the limit as x approaches 1 of just x plus 1. We can then do a direct substitution, 1 plus 1, and say it's 2. Because we're using this function everywhere except 1. And if all we're doing is approaching 1, I only care about using that piece of the function. I don't care about what's going on at 1. All right, what about this one? Okay, right away, if we try direct substitution, we take 0, we plug it in for h. Notice what we get. We would have 3 squared minus 9 over 0. That's 0 over 0, which again, we say is an indeterminate form. So when it's indeterminate, when it's specifically 0 over 0, you may be able to manipulate things algebraically to be able to find a limiting value. You should try that, and if all else fails, you can always use your calculator and use the table to see if a limit exists, like we did in the first example. All right, well, in this case, I can multiply the numerator out and simplify. And when we FOIL that out, that's going to be 9 plus 6h plus h squared minus 9 over h. Notice the 9's now cancel out, and we're just left with 6h plus h squared over h. Then we can divide an h out of everything, and we have this limit. the limit as h goes to 0 of 6 plus h. And it's okay to call these equivalent because we're talking about limits, not the functions. These are this 6 plus h is technically not equal to this, but only because they have different values at 0. Since all we're doing is approaching 0, it's okay because of that first property we wrote down to say their limits will be equal. And now we can try a direct substitution. 6 plus 0, which is 6, and I'm done. All right, so this is just a restatement of something we already knew, which is that the limit of a function as x approaches a equals L, if and only if the limit from the left and the limit from the right as x approaches a also equal L. And so as a reminder of that, let's talk about the absolute value function. Well, any absolute value function can be defined as a piecewise function by breaking it up on its domain. So specifically, the way an absolute value function is, the parent absolute value function works like this. If x is less than 0, if x is negative, then the absolute value will return the opposite of x. So think of negative as meaning opposite. So if I plug in a negative value for x, then we want the absolute value to return the opposite of that value, which would be positive 3 in that case, right? All right, and then if x is positive, so if x is greater than 0, the absolute value just returns x itself. So when I'm evaluating the limit for this, so the limit as x approaches 0 of the absolute value, I need to evaluate it in two parts. I need to look at what's going on the left and the right. So as I approach 0 from the left, well, the numbers to the left of 0 are negative. So I'm looking at only this piece of the domain, which means I'm only looking at this function. So I could then say that equals the limit as x approaches 0 from the left of opposite of x. That's what that piece of the function does. Now we can just do a direct substitution. In terms of direct substitution, you don't deal with one-sided limits any different than you would deal with a normal limit. You still just plug in the value. So I end up with negative 0, which is not a thing. It's still just 0. Okay? So now let's look at what's going on as we let x approach 0 from the right. When I go up to my piecewise function, if I'm plugging in from the right, I'm coming in from positive values of x, so I want to use that piece of the function, just the x. So that's going to be equal to the limit as x approaches 0 from the right of just x. And again, we can just do a direct substitution, which is just 0, and we're done. And notice we got 0 as x approached from the left and 0 as x approached from 0 from the right. Therefore, the overall limit exists and is also equal to 0. Okay, likewise, we can prove that this limit does not exist, and we're going to kind of do it the same way. We're going to break it up on its domain. So I'm going to say, okay, let's let f of x equal the absolute value of x over x, which if we write it as a piecewise function, if x is less than 0, remember that the absolute value will return negative x. So I'll have negative x over x. And if x is greater than 0, my absolute value returns positive x. So positive x over x. Well, notice then that my numerator will reduce to negative 1. My denominator will reduce to 1. Negative 1 if x is greater than 0. or sorry, less than 0. And 1 if x is greater than 0. Well, then the problem becomes, okay, well, if I want to evaluate the limit as x approaches 0 of absolute value of x over x overall, I need to look at what's going on the right hand versus the left hand side. So if I approach from the left, I get absolute value of negative x, absolute value of x over x. What part of the domain in the piecewise function am I looking at if I'm approaching from the left? We're looking at negative values, right? So it's just going to simplify to -1. Limit of a constant is a constant, so it's -1. Then if I let x approach 0 from the right, what piece of the domain am I on? I'm on the positive side of 0 because I'm approaching from the right. So I'm using that piece of the function. So the limit as x approaches 0 from the right of 1. Limit of a constant is a constant. Now my left-hand limit and right-hand limits don't approach the same overall value. So we say that the limit does not exist. Okay, and I'm just throwing a bunch of different examples at you. This is going to be the last one I go over, and then I'm going to give you a student example. Here again, if I just tried to do a direct substitution, we would end up with 0 plus 9 under the square root minus 3 over 0 squared, which is 3 minus 3 over 0, which is 0 over 0. This is indeterminate, so not necessarily true that the limit does not exist. It's just in a form right now that we can't make a direct substitution to figure it out. So you could pop that function into your calculator, use a table, and approach 0 closely from both sides. See if you can find a pattern, but we can also do this one algebraically. With square roots, we try and use, again, the difference of squares to kind of exploit its relationship, and that was this. A plus b times a minus b will always multiply out to the form a squared minus b squared. These things are called conjugates of each other. So it's a binomial where you have the same terms separated by the opposite sign. So a plus b is a conjugate of a minus b. We kind of want to use that relationship here. And this goes for, oftentimes, this is a technique you can use when you have a square root with your indeterminate form. I'm going to multiply this by its conjugate. So its conjugate being t squared plus 9 plus 3. And that's okay to do as long as I do it to both the numerator and the denominator, because then I'm not fundamentally changing the fraction. I'm really just multiplying by 1. And so the thing is, don't try and multiply this out by hand. We know what the pattern is going to look like. Think of this guy as a and this is b, right? So it's going to multiply out to a squared minus b squared in the numerator. So a squared, you would just be getting rid of that square root. So I just am left with t squared plus 9. And then minus b squared, so minus 3 squared. 3 squared is 9, so minus 9. The denominator, we're going to leave it in a factored form. Don't try and multiply things out. It's going to be counterproductive because what we're going to try and do is cancel things out wherever possible. And you can only cancel in a fraction when it's already factored, so just leave it like this. All right, so next we're going to try and simplify that numerator as much as we can. The 9's cancel out. I'm left with t squared over t squared times the quantity root, t squared plus 9 plus 3. Now I can divide out t squared. And so what we're left with is an equivalent function just written in a new form. Root t squared plus 9 plus 3. So now let's take a look at my limit one more time. So I'll say the limit as t approaches 0 of 1 over root t squared plus 9 plus 3. So now if I try and do a direct substitution, does it work out? I have root 0 plus 9 plus 3, which is 1 over 3 plus 3, which is 1/6. Oh, sorry. Got my picture over the answer. So that's it. So that technique, multiplying by the conjugate, is really useful when you have a fraction that involves a square root and it's giving you an indeterminate form when you try and make a direct substitution. All right, all that in mind, go ahead and give this student example a shot. We will go over it in our next class. Good luck.